Hello students, welcome to the third class of the sets. In this video lecture, I will be discussing the concept of subsets. So let me to define the subset. So how can I define the subset? So if A and B are any two sets, then I will call A to be the subset of B. When can I say that A is a subset of B? If every element of A is an element of B, right? So if this thing holds, then I say A is a subset of B. So it is denoted as A is a subset of B. For example, if I say A is 1, 2 and B is 1, 2, 3, 4. Now, can I say A is a subset of B? Why A is a subset of B? Because 1 is an element of A which is also an element of B. Similarly, 2 is an element of A which is also an element of B. So, when I can say A is a subset of B, if every element of A is also an element of B, right? So that is the definition of a subset. Now, so note, when A is contained in B, that is A is contained in B. So how can I say that? That is A is contained in B, right? We can say in this way also, or the other way is we say that B contains A, right? So that is the way how can I pronounce this? A is contained in B. And A is called the subset and B is called as the superset. Fine with this? Now, very important remarks. So the first remark is every set is a subset of itself, right? So you have to remember this, that every set is contained in itself for all A. For example, if I say A is 1, 2, right? And again, if I say B is a subset which is A only, right? So now I have to show that every set is subset of itself. Clearly, 1 is a member of this, it is also a member of this. 2 is a member of this, it is also a member of this. So every set is a subset of itself. So this is a very important remark that you should remember. The second is null set is a subset of every set, right? So this thing also you should remember, that empty set is always contained in the set. So this is something which is very trivial, right? So null set is a subset of every set. Then now the next important remark is, if I give you some set having maybe 2 elements or 3 elements or 4 or finite number of elements, so is there any way to calculate the total number of subsets? Yes, there is a way. So the total number of possible subsets of a given set containing an element is nothing but 2 raised to power n. So that is a formula to calculate the total number of subsets. For example, if A is 1 and 2, so the total number of possible subsets will be 2 raised to power 2, that is 4. So there will be 4 subsets, and 2 subsets I have already defined above. So that is first is empty set is always contained in A, and second is A is contained in itself. So 2 subsets are there, and what about 2 more, because and fourth. So that will be singleton 1 and singleton 2. Fine with this? Now moving on to the next definition, that is a comparable sets. So when can I say the two sets are comparable? So two sets are said to be comparable if this condition holds, that either A is contained in B or B is contained in A. So whenever such a situation happens, then we say that the two sets are comparable. Now moving on to the definition of a proper subsets, right? So we have said that empty set is a subset, A is a subset of itself. So those were the sets, right? If I say A is a subset of itself, right? A is a subset of itself. So in that case, when I will ask you what is the subset of A, you will say that is A itself, that is A is equal to A only, right? So what do you mean by proper subset? When I say proper subset, let me to take an example. For example, if A is 1 and 2, right, and if I calculate the subset, so they will be total 4 subsets. Why? Because as we have calculated in the above formula, 2 raised to power n, and here it will be 2 raised to power 2, which is 4, right? And the 4 subsets will be, one is a singleton 1, one is singleton 2, then is an empty set and A, right? You can see that this is a subset, right, which is exactly equal to A, right? So when I am going to ask you about the proper subsets, you will just choose all the subsets which are properly contained, right? So if A is contained in B and A is not equal to B, so the equality must not hold, right? So if I ask you what are the proper subsets, so you will say that this singleton 1 and this singleton 2, they are the proper subsets. Fine. So they are known as the proper subsets, right? So a non-empty set, and mind it should be non-empty. So what about this empty set now? So it will also not come into the case of proper subsets. Why? Because in case of proper subsets, you have to consider only those sets which are non-empty. So if A is a non-empty set of A, it is said to be a proper subset of B if there is at least one element of B which is not in A. Fine with this? So there must be at least one of the elements. So if I say that this is my, so let me to call this as A and let me to call this as B. So if I say A is a proper subset of B, right? A is a proper subset of B. Can I say this thing? Yes, I can say. Why? Because there is at least one element in B. So what is that element? That is a 2, right? Which belongs to, that is a 2 belongs to B, but 2 does not belongs to A. So in that situation only you will say that my A is a proper subset of B. Fine with this? And so the next question that must arise in your mind is that what about empty set and the set itself? How we will call them? Because all the other sets except empty set and the set itself, they will come into the category of proper subsets. Fine with this? So empty set and the set itself, they will come under the category of improper subsets. So how can I define improper subsets? So if the subset is not proper, it will go into the category of improper subset. And example, that is A is contained in A and phi is contained in A. So they are always the improper subsets. And in some books, they are also written as trivial subsets, right? So they are the trivial subsets. Moving on to the definition of a proper set. So the collection of all the possible subsets of a given set is known as the proper subset, and it is denoted as P of A. And we know how to calculate the number of elements in power set, that is nothing but 2 raised to power n. Now let me to take an example in order to make you this thing more clear. For example, if I choose A to be ABC, so the total number of elements in A, that is 3. So how many elements will come into the power set? That is number of elements in power set, that is 2 raised to power 3, which is 8. So 8 elements will come. So let me to call them B1, B2, right? B3, B4, B5, B6, B7 and B8. Fine with this? So what, in total there will be 8 subsets, right? So let me start with from B1. So that is a singleton A. Let me to call B2 as singleton B. Then this is singleton C. Then take the doublets, that is AB, right? Next will be AC. Next will be BC. Fine. And the 2 will be, that is empty, and the set itself, that is ABC, which is nothing but A only. Fine. Now moving on to the definition of a universal set. So if there are some sets under consideration, then the sets of each of this is a subset. So this is called as a universal set. It is denoted by U, X or E. So let me to take an example in order to make you things more clear. For example, if I say I have a set of integers, right? So integers are contained in what? Integers can be contained in rationals, or integers can be contained in reals, right? So these can be called as the universal set in reference to the given subset. So whenever you have to define the universal set, you will always consider a reference subset. For example, in this the reference subset is Z. So in case of Z, the universal set can be Q, it can be R, or it can be complex also. So can I make a remark that the universal set is not unique? Fine with this? Moving on to few illustrative problems so as to make you all the things more clear. So consider the following sets. So that is phi A, which is equal to 1 3, B, which is equal to 1 5 9, C, which is equal to 1 3 5 7 9. Insert the correct symbol which is contained in. So this is contained in and this is not contained in. Fine, this is not contained in. So you have to insert that symbol. So what will be the symbol that will come under this? Phi is contained in A or not? We know that every set is a subset of itself. So yes, phi will be contained in A. Next part. Is A contained in B? So what is your A? A is 1 3. And what is your B? That is 1 5 9. So if A is contained in B, it means every element of A should be an element of B. So 1 is an element of A, which is also an element of B. So true. But what about 3? 3 is a member of A, but it is not a member of B. So I will say A is not contained in B. So not contained in B. So moving on to the third one, that is A and C. So what is my C? C is 1 3 5 7 9. So let me to write C here. So now can I say A is contained in C? So if this thing is true, so it means every member of A should be a member of B. So that is a true, because 1 is a member of A, which is also a member of C. 3 is a member of A, which is also a member of C. So in this case, I will say that A is contained in C. And the last part, that is whether B is contained in C or not. So if B is contained in C, so every member of B must be a member of C. So 1 is contained here, which is also contained here. Similarly for 5 also, and similarly for 9 also, right? So in this case also B is contained in C. So I hope this problem is clear to you now. Moving on to the next one, that is list all the subsets of the set. So we can see the number of elements in this set are 3. Fine. So the all subsets will be, that is a power set, right? So the power set will contain total 2 raised to power 3, that is 8 elements. And what are those 8 elements? So that is, first element will be, right, empty set, then it will be singleton -1, singleton 0, singleton 1. Then take the doublets, that is -1 comma 0. The next will be -1 comma 1. The next can be 0 comma 1, and the last will be, that is -1 0 1, that is the set itself. And you can easily verify, or you can easily count, they are 8 in number. Moving on to the third problem. So we are given a set A which is having the element PQRS. B is a set which is having element PQR, and C is a set which is having the elements Q and S. Find all the sets X such that X is contained in B. So like, in order to find out the sets, right, which are contained in B, or the sets which are contained in C, so let me to find out the power set of A. Fine. So let me to define the power set of A, power set of B, and the power set of C. So in, you can easily see that A is having 4 elements. So the total number of elements in the power set will be 2 raised to power 4. So the total number of elements will be 16. Similarly, in power set of B there will be 8 elements, and in power set of C there will be 4 elements. So let me to write the power set of A. So that will be having, that is empty set, singleton P, then singleton Q, then singleton R, singleton S, right? So follow the same pattern. Then the doublets, that is PQ, it will be PR, next will be PS, then it will be QR, the next one will be QS, and the another one, that is a RS, next one will be PQR, right? And the next one is, that is QRS. Fine. Another one, that is a PRS, another one, that is PQS, and the next one is PQRS, that is a set itself. So they are the power sets of, that is a A. So these are the power sets of A. Now similarly I can define the power set of B also, and the power set of C also. So the power set of B will be, that is empty set, then there will be singleton P, singleton Q, right, and then it will be singleton R, then it will be doublets PQ, right? So make the doublets, then it will be PR, right, and then it will be QR, next one will be PQ and R. Fine with this. So they are the power sets of B. Now let me to see the power sets of C. So what can be the power sets of C? So they will be, that is an empty set first of all, then it will be singleton Q, singleton S, and the doublet QS. Fine with this. Now what I was asked that X is contained in B, right? So when I have to find X is contained in B and X is contained in C, so it means X must be an subset of B and C, right? So this implies X is a subset of B and C. Fine with this, because that is a given. So it implies X must belong to power set of A and X must belong to the power set of C. So now you just find out all those sets which are in power set of A also and which are in power sets of C also, right? So just see, first one will be, that is a empty set, right, that is contained in both of these. And what about any other element? Yes, there is a singleton Q here also and singleton Q here also, and there is no other X which is satisfying this property, that is X belongs to power set of A also and X belongs to power set of B also, and hence I can say that my X is nothing but, that is a empty and singleton Q. Now the next problem is, let A, B, C be the three sets. If A belongs to B and B is contained in C, is it true A is contained in C? If not, then we have to give an example. Let me to consider a counter example. Let A be equal to singleton P. B and C, you can choose them to be, that is a singleton P and Q, right? So A is having, that is a singleton P which is also a member of B. So clearly A is belonging to B. And is B contained in C? Yes, every set is contained in itself. So these two properties which are given to us in the question, they get satisfied, right? Now I have to check, is it true that A is contained in C? So now, is A contained in C? That is the next question. Can I say A is contained in C? No, this does not hold. Why? Because C is singleton P, that is a contained in this. This thing does not hold. Why? Because P is a member of P belongs to A, but P does not belongs to this C, right? This C set does not contain P. It is containing that is a set of singleton P, not P element, right? So A is not contained in C. So moving on to the last problem, that is prove that A is contained in B, B is contained in C, and finally you have to show that A is contained in C. So that is what we are interested to prove, right? And remember students, whenever you have to show the containment in mathematics, firstly you will choose any arbitrary element. So choose any arbitrary element from A, and finally show that the particular element belongs to B. So if you are capable enough to show this thing, then you can say that A is contained in C. So follow the same approach. So A is contained in C. That is what we have to prove. So now you will consider any element. So let A be any element, small a be any element that is from A. Now it is given to me in the question that A is contained in B. Given A is contained in B. So if A is contained in B, it implies that A should also be a member of B. Now because B is contained in C, so can I say A is also belonging to C? Right? So have we proved this thing? So we have chosen any arbitrary element from A, and then we have finally shown that that arbitrary element was also member of C. So hence we will say that A is contained in C. So that is the standard approach. Whenever you have to prove the containment in mathematics, you will always use this concept. So I hope this video lecture is clear to you now. If there are any doubts, you can mention your doubts in the comment section. For more such videos, do subscribe to my YouTube channel and do not forget to press the bell icon. So I hope you have enjoyed this video session. Thank you for watching. Thank you very much.